Now we are going to the presentation of Professor Zornberg. Professor Zornberg has over 35 years of experience in practice and research in geotechnical and geosynthetics engineering. His research focuses on transportation in geotechnics, environmental geotechnics, geosynthetics, unsaturated soils, and expansive clays. As an engineer consultant, he has been an expert witness in litigation and forensic geotechnical cases. From 2010 to 2014, Professor Zornberg served as president of the International Geosynthetics Society, IGS. He has authored over 500 technical publications, written several book chapters, and been awarded 3 patents. Professor Zornberg received numerous prestigious awards, and in 2019, the IGS established the Zornberg Lecture, recognizing his contributions to the discipline of geosynthetics. Professor Zornberg, we are delighted to have here with us. Thank you very much for coming, and you have the floor.
Very good. Can I use this? This one is fine. Thank you so much for the kind introduction. It is such a pleasure to be here and talking about education within the geotechnical context. So the topic of my presentation is different than that of Jennifer. Jennifer did talk about a paradigm change. I'm going to talk about content. However, there are some elements that are common. For example, she did talk about a newcomer to geotechnical education, and I'm also going to talk about a comparatively newcomer to the geotechnical content. And the newcomer is geosynthetics. And I'm going to be talking about geosynthetics in the classroom and how to get ready for incorporating them. And I'm going to be very specific. I'm going to be talking about undergraduate education. So first, why geosynthetics? I could say that there is a term that I like to say about geosynthetics, and I could say that they are ubiquitous. So they are essentially used in nearly all subfields of geotechnical engineering. Now, it could be argued that when it comes to the point of applications, there is a good number, fair amount of programs that would prepare professionals to use geosynthetics after even they have graduated. But I could contend, I could argue that the initial exposure to geosynthetics belongs to a more fundamental level at the undergraduate education. So the proposal in here is to introduce, even if very briefly, the concept of geosynthetics within the family of geomaterials. We could argue that soils and rocks and geosynthetics belong to the geomaterials. And as such, they have unique properties and unique characteristics way before we start talking about applications or geotechnical projects. Now, I could argue as well, and I will give you some examples, that the teaching of geosynthetics can also help us provide some additional context and strengthen the teaching of natural geomaterials, that is, of soils. Before we get started, I would like to give a very, very brief overview of terminology, just to make sure that at least Jennifer that may not know what the different types of geosynthetics are. I'm sure that you all do, but let me walk you through a number of jargon, terminology aspects that I would like for you to, that I may use during the presentation. There is a broad, one of the characteristics of geosynthetics is their breadth, and we have many different types. Geotextiles, this is a textile, but if it is not used in a geotechnical project, it's not a geotextile, it's just a textile. A geotextile is an industrial textile, and what makes it a geotextile is that it's used in geotechnical projects. Geogrids, geomembranes. I'm not going to tell you what they are, I'm just going to tell you their names. Geonets, Geocomposites, more than one geosynthetic in a single product. Geocells. This is probably one of the few non-two-dimensional geosynthetics. Geosynthetic clay liners. These are composites of geotextiles with bentonite, erosion control products, and many others. In addition to the geosynthetic types, I need to tell you about the geosynthetic functions. And this is key. This is key to the understanding of geosynthetics, and I believe that is another important contribution that the geosynthetics may bring to geotechnical engineering at large and to the understanding of soils. What are the geosynthetic functions? This is what are we going to use geosynthetics for. We can talk about some mechanical functions of geosynthetics, including separation. We are going to use geosynthetics to maintain different materials, different geomaterials, different soils separate. And reinforcement. We're going to develop tensile forces, but in order to minimize problems related to stability. And stiffening. And also we're going to develop tensile forces, but in this case to control deformations. And then we get into the blue geosynthetic functions, the hydraulic ones. We're going to talk about filtration. In this case, we're going to be talking about flow across the plane of geosynthetics. We want water to get through very easily, as in any filter, as in a granular filter. We do not want particles to go with them. And barrier, we want to prevent the infiltration of water. And drainage, we want the flow of water across within the same plane of the material. And protection, we want to minimize problems associated with the defects that the contact of two materials. For example, a gravel in contact with a geomembrane, we need to protect them from defects. All right, so we talked about, very briefly, about types of geosynthetics and their functions. So I want you to get to a survey before telling you that we need to get a better exposure of geosynthetics at the undergraduate level. I want you to get into a survey on how much of this we're already doing. But I stumbled into, before knowing how much are we exposing undergraduates to geosynthetics, I had to understand what is the structure of geotechnical engineering in civil engineering programs. So before telling you about geosynthetics, I'm going to tell you something broader, and that may be relevant for many of us in this conference, which is, where does geotechnical engineering fit within civil engineering? So I conducted a survey, and the goal was how geosynthetics are taught, but we are first going to get into how geotechnical engineering is taught. So I'm very, very pleased. I have 9 countries that I selected, and I relied on volunteers to give me the right contact information for these countries. And the response rate was great, an average of about 73%, which is stunning. I insisted in many cases. But the majority of the participants, I was in doubt whether to analyze or to filter the data between non-PhD granting institutions and PhD granting institutions. It turns out that the great majority were PhD granting institutions to begin with. So I'm going to present the data without filtering them according to the different types of institutions. And as I mentioned, the analysis that I'm going to present are 2. First, how do geotechnical courses fit within civil engineering programs? And after passing through that, I'm going to talk about how geosynthetics coverage is done or not in geotechnical courses. All right, so these are the countries. And I had to divide the countries in 2 big groups. One are those countries in which the predominant majority of institutions grant civil engineering degrees in 4 years. And this includes Canada, India, Turkey, and the US. Very high responses rate, and this gives me confidence that the data that I'm going to show you is representative. But then I'm also going to cover countries where the predominant number of degrees are civil engineering degrees are offered in 5 years. And this includes Argentina, Brazil, Colombia, Germany, and Greece. A fair amount of countries. So let me tell you. First, and I divided the world, and I think that a topic of research, and Jennifer was talking about threshold. What is the minimum content, geotechnical content, that all civil engineering, future civil engineers should have if they are going to be called civil engineers? And the answer is not obvious, because you're going to see that there is significant discrepancies, and more importantly, I think that the trend is to shrink and shrink and shrink the content in geotechnical engineering. So what is the minimum geotechnical engineering content that civil engineering programs should offer? And because of that, I divided the world of courses into mandatory courses and elective courses. Mandatory courses are those that all civil engineers will receive. Elective courses are those that decide to specialize will receive. In the four-year programs, what is a fraction of institutions that said how many mandatory courses in geotechnical engineering they receive, the students receive? All of them in Canada, or 63% of the institutions in Canada, offer at least 2 mandatory courses in geotechnical engineering, which is quite good for a 4-year program. And that's consistent with India. 64% offer at least 2 mandatory courses in geotechnical engineering. Then we get to Germany, to Turkey, even better, because essentially 100% offer at least 2 mandatory courses in geotechnical engineering. And the big problem is the US. In the US, I consider staggering. A staggering 7% of institutions do not offer mandatory geotechnical engineering courses to their students. So, a student may graduate as a civil engineer without receiving any exposure to geotechnical engineering. The rest, and 54%, the great majority, receive 1 mandatory course in geotechnical engineering, and then we have 2. This is 4-year programs. Let me show you, again, mandatory courses, but now in 5-year programs. As a reference, I'm showing you here, there. How does this work? Here. Here. So as a, no. Okay. You have as a reference a previous graph. And now I'm going to show you the 5-year programs. So Argentina, 5-year programs, but not significantly better coverage in terms of mandatory courses in geotechnical engineering. 58% teaches 2 mandatory courses in geotechnical engineering. Much better in Brazil, 56% or more, and Colombia offer 3 or more mandatory geotechnical engineering courses. When it comes to Germany, we're again back to 2, which is not that different in terms of mandatory exposure to those in 4-year programs. And then the outlier is Greece. The outlier is sometimes in the good sense, sometimes you're going to see in the very bad sense. 100% of the programs surveyed in Greece offer at least 3 mandatory courses in geotechnical engineering. Okay, so here I'm going to just regurgitate a little bit what I just showed you. So there is a predictable but clear pattern. Programs with longer duration tend, but not necessarily do have, more mandatory courses in geotechnical engineering. Sadly, some four-year programs even lack a single mandatory course in geotechnical engineering. Now, I would contend that we cannot fight, and also in my informal review, I believe that many countries are going from 5-year programs to 4. Some countries have gone from 6 to 5. The tendency is to shrink the length of the civil engineering program. And we cannot reverse that. I could say, rather than fighting that, as geotechnical engineers, we need to adapt. So we need to adapt to the trend of decreasing the length of civil engineering programs. And we need to adapt to that. And this shift is irreversible, but certain topics need, and maybe I'm back to the concept of threshold that Jennifer was mentioning. What is the minimum that we expect civil engineers to receive in terms of geotechnical engineering, including some subspecialties within geotechnical engineering, such as geosynthetics? Okay, so this is mandatory. To be fair, but it's more difficult to interpret, I'm going to also show you data on the elective. A number of elective courses in geotechnical engineering, but this is harder to interpret without keeping in mind what, in context, how many mandatory courses have been observed. But I think that we can draw some conclusions. Elective undergraduate geotechnical courses in Canada, I could say a dual, either almost nothing, no additional geotechnical courses, or potentially more than 5 additional technical elective courses, a fair amount, a healthy amount in India. We have 5 years, so we can, we're compensated, we're in 4-year programs, so we're compensating for the small number of mandatory courses. In Turkey, also a healthy number of electives, and also is in the US. Quite similar pattern in all 4-year programs in terms of elective and geotechnical engineering courses. Let me show you about 5-year programs. Again, I show you here the snapshot of what I just showed you. So in 5-year programs, the same way that the previous in 4-year programs is quite consistent across programs, in 5-year programs is quite diverse. The number of elective courses, geotechnical courses, varies a lot, from essentially none in Argentina. Red means bad. Red is bad, is 0. No elective courses. To a healthy number in Brazil and Colombia. I would say bad again in Germany, and off the charts goes for Greece. So over 50%, over 70% of the programs offer at least, in addition to offering, if you remember the previous chart, 100% offered a significant number of mandatories. In Greece, we have a fair amount of also electives, above and beyond the mandatory. Okay, so a few conclusions, and again, I'm not going to get in detail. This is just highlighting the previous trends. And I think that in the 4-year group, most but not all institutions report offering at least 1 and most likely 2 technical electives, a quite uniform pattern. When it comes to 5-year programs, in some cases, we have a smaller number than at least the 4-year program in terms of technical electives. In some cases, we have more. I could say quite dissimilar. And again, so in some cases very small, in some cases comparatively large. All right, so after I told you a little bit about the pattern of what are we offering our students in terms of geotechnical engineering, and before getting into what are we offering of geosynthetics within those programs, let me get you on why are we talking about geotechnical engineering. So there is a need, I would say that they have become essential in modern civil engineering programs. I would say, unlike natural soils, geosynthetics have tightly controlled properties. I would call them geotechnical engineering properties, and that gives us an edge in trying to teach those properties to geotechnical engineers. It could be argued that the topic of sustainability is more and more important, and there is a lot of research indicating that when using geosynthetics, we end up with using less amount of aggregates, thinner structures, and consequently, typically, we will end up with lower carbon footprint when the solutions are involving geosynthetics than in alternative solutions do not using geosynthetics. And I could say that we're not talking about something that cannot be done. It's definitely feasible, and I will show you some examples. And it's scalable. And by scalable, I mean that you can offer just very little or decide to offer more. But it's very doable, and you can choose what is the right size and fit for your program. So, for example, from time to time, I'm going to show you teaching samples of slides that I use in my courses. So, for example, I tell my students that the use of geosynthetics in geotechnical projects can be in extremely important projects. What I'm going to show you here is what I understand is the tallest geosynthetic reinforced wall in the world. It's in Sikkim Airport in the Indian Himalayas. And we're talking about a structure that is 80 meters tall, 80 meters tall. And it's so tall that it's even hard to take a good picture of it. So for example, here we see in this picture 3 terraces of the retaining structure. What you do not see is that there are 2 additional terraces that I'm not showing you here. And what you also do not see is that this picture was taken during construction, so there are 3 additional terraces in this structure. A massive retaining structure. Again, as far as I understand it, is the tallest reinforced soil wall in the world. However, the same way that we have these massive structures, we have everyday structures. This is near my home in Austin, Texas. And driving by, you can have very simple, unremarkable, I could say good-looking retaining structures that are the ones that we can design in regular projects. So that's why we should teach geosynthetics, but let's recognize that there are challenges in incorporating geosynthetics in the curriculum. First, I just mentioned curriculums tend to shrink in length, and the number of topics that we are necessarily adding continues to increase. So, and I could say that, okay, since I'm struggling with what to fit, an easy cut is not to teach new stuff. So never mind that the new stuff is very relevant, but I need to cut stuff. So the first thing to cut are the newcomers. And I could contend that that's not necessarily the right approach. The other is faculty readiness. These are well-established geotechnical solutions, but many of us, including me, didn't receive a formal teaching in geosynthetics in our own curriculum, so I may not feel extremely comfortable in teaching it myself. I'm not an educator, I'm an engineer, so my main basis for how I teach is how I was taught myself. Now, there is a significant breadth, and I told you so many different names on so many different functions, and this is a challenge when exposing students to geosynthetics. However, these challenges, because of these challenges, there are solutions, and this answer is the teaching can be strategic, and I'm going to show you some examples. But the same way that there is a need, there are challenges, but there is an appeal. There is an appeal to teach geosynthetics. I may be biased in what I'm going to tell you, but I would say that geosynthetics may inspire the new generation of geotechnical engineers or civil engineers to do what they wanted to do to begin with when they chose engineering, which is to focus on ingenious solutions. Ingenuity, I could say, is a term, a qualifier that I typically use when referring to solutions involving geosynthetics. The same breadth of geosynthetics that I mentioned as a challenge is also an appeal. And teaching geosynthetics, I believe that offers the opportunity to bring new material to refresh the curriculum with content that is modern and engaging. So, how I'm doing with time? In order to tell you about the appeal, and considering that an important focus in this conference is on teaching unsaturated soils, let me give you two examples. Typically, this is something that I would cover more certainly not in the first exposure to geosynthetics, more at the applications level. But let me tell you about two applications of geosynthetics that may not be obvious. One, and I'm going to talk about unsaturated soils. One is using geosynthetics as a barrier to unsaturated flow. And I'm going to give you a second example. Using geosynthetics as a drain to convey unsaturated flow. Very challenging projects. Both of them, and that's why I'm going to tell you about the appeal of these projects. So I'm going to tell you about two projects that focus on the appeal of, illustrate the appeal of teaching geosynthetics, and now within the context I chose two cases, both of them on unsaturated soils. First, let's talk about unsaturated soil barriers. I'm going to take you to Denver, Colorado. What you see here, let me make sure that it's working. I think it's run out of battery. Okay, what I'm showing you here is Denver metropolitan area. On your upper right northwest, you see the international airport. There are many different ways in which you can say this is the largest airport in the US. Denver claims to be the largest in terms of size, area, footprint. And the other big patch that you see is this green patch. That's the Rocky Mountain Arsenal. That's the Rocky Mountain Arsenal, and I'm going to be talking about a barrier for the Rocky Mountain Arsenal. And what was the challenge? To transform this Rocky Mountain Arsenal, a big area, into what is now the largest urban wildlife refuge in the US. But it's a highly contaminated site. How? And this is a trick. By using, or part of the solution involved using geosynthetics as capillary barriers to enhance the ability of the cover systems. We're going to encapsulate hazardous waste, and we do not want water to infiltrate into the hazardous waste. And we're going to do that by characterizing these under unsaturated conditions, including using a capillary barrier. So this is a huge area, almost 70 square kilometers. And why is this important? Well, at one point, these are 27 square miles. One of those square miles at one point was identified as the most contaminated square mile on Earth. This is the site where months after Pearl Harbor, the US initiated the manufacturing of chemical weapons, sarin gas. So I'm going to talk about the remediation of this site, and during the remediation, sarin bomblets were identified even at that point. There are many different projects within this site that were part of this major project, including some of the projects, essentially hazardous waste containment facilities, triple-lined hazardous waste containment facilities that were constructed on site. But the one that I'm going to focus the most is after all the hazardous waste was consolidated into hazardous waste containment facilities, the soils were contaminated. Huge areas were contaminated. Soils were contaminated. And these soils had to be covered. And the way to be covered was with, Denver is a semi-arid area, so the concept of evapotranspirative covers was considered. What is an evapotranspirative cover? Is essentially letting water come from the sky, and the water under unsaturated conditions starts to infiltrate, but before the water, the infiltration front reaches the waste, evapotranspiration comes in a dry season and removes that back to the atmosphere. That's an evapotranspirative cover. But that was not enough. That was not enough. So instead, we needed additional sources for storage. And what I'm showing you here is in the vertical axis depth, in the horizontal axis volumetric moisture content. So during the wet season, the moisture increases on the surface, and you see an advancing moisture front, and the advancing moisture front reaches the base of the cover. So in principle, this is failure if this was an evapotranspirative cover. But it's not an evapotranspirative cover. It's a capillary barrier. So there is additional storage capacity that is essentially under unsaturated conditions. Essentially, we create a barrier with unsaturated conditions. And in here, I'm showing you a coarse-grained soil or a geotextile. The same way that coarse-grained soils, gravel, under unsaturated conditions are barriers to clays. The same goes with geotextiles. Their open pore structure creates a capillary barrier that allows additional moisture accumulation in this system before again, now is the green profiles, the moisture recedes once the dry season comes back. And here's a view of the cross-section, quite a complicated cross-section, but among the different components, I'm going to highlight a non-woven geotextile that works as a capillary barrier to promote the storage capacity of the system. So the next time that you go to Denver and you come back from the airport and there's nothing over there, there is something. You drive and you see nothing. You're driving by the Rocky Mountain Arsenal, and you can get in right now and get to appreciate bisons. And actually, the importance of this site is that you see Denver at the background. So what is the significance? The geotextile unsaturated soil barrier was recognized as an essential component in the cover system. This increased the storage capacity. And why does it work? Because of the contrast in pore sizes that can be offered by clean granular materials, or in this case, by the open structure of geotextiles. Okay, I gave you one example of a case history to show you the appeal, and again, in an unsaturated soil problem. Let me show you another unsaturated soil problem, but the opposite. Instead of talking about a barrier, I'm going to focus on a drain, to drain water under unsaturated conditions. I'm going to show you another case, the Daniel Boone Bridge in Missouri. Essentially, the problem here was a very high water table. Water reaches, there was a bridge and an approach road that had to be constructed, and capillary moisture reached the structural cross-section of the road, and this is not good. Water is not good for structural capacity in roadways, so this had to be drained. There are many different sources of water, but in this particular case, we are going to focus on sources of water coming from the groundwater and reaching our site by capillary rise. How it was solved using what is called a wicking geotextile. I'm not going to get into the details, but after evaluating many different structures, this was to reconstructing a bridge in the Missouri River, and essentially there were high water table. There was a high water table, and this is a cartoon of the solution. The idea is that water reaching the structure from the water table would reach this weakening geotextile, and this could drain under unsaturated conditions to the edge of the structure, keeping the integrity, maintaining the integrity. Again, draining water under unsaturated conditions is tough. Draining free water is easy. You just put a drain. Draining water under unsaturated conditions is very tough. But here we have a view of the construction, and here you have a view, even during construction, of how this water was draining. So, I didn't tell you how this works. So the significance was that the adoption of geosynthetics with enhanced lateral drainage avoided the need of costly granular materials. The structure is performing very well. Why does this work? Well, there is a new concept in the geosynthetics community that is called suction-driven flow. What is this? Here you see an electron microscope of the fibers. These are not circular fibers. These are not rectangular fibers. These fibers have grooves. These are hair-thin fibers. So what you see here is typically the way that geotextiles are made. You have a number of, this is a geotextile sample, you're going to have a number of yarns. That's not the flow that I'm talking about. Within each yarn, we have a number of fibers. That's not what I'm talking about. Is within each fiber, we're going to have a number of grooves. Under unsaturated conditions, all the pores are going to be filled with water. That's not what we're talking about. What we're talking about is draining water by capillarity, the very basic concept of capillary tubes, but in this case is capillarity through the grooves of the fibers. All right, so two examples to illustrate the appeal of geosynthetics, promoting innovation and promoting ingenuity in the design of geotechnical projects. But in addition to that, about the importance of geosynthetics in the geotechnical engineering field, I could argue that geosynthetics can also strengthen core geotechnical concepts. And this comes back to the concept of functions. Geotechnical soils have different functions when we use them as construction materials, but we do not think of them as having functions. We talk about properties, but we do not group the properties into functions, which is what we do in geosynthetics. And this is a concept that we can borrow, particularly when using soils or geomaterials in general as construction materials, which is an enormous fraction of the geotechnical projects that we have. I recognize that a big fraction of the projects that as geotechnical engineers we do is subsurface investigation. That's not what I'm talking about. I'm talking about the use of geotechnical materials as construction materials, to build dams, to build embankments, to build roadways, to build retaining walls. For example, how are we going to strengthen the knowledge of flow through soils? And I'm going to get back to this topic again, the learning about reinforced soil interaction can help us understand the shear strength of soils. After going over why we teach geosynthetics, let me go back to the survey. And we learned about the structure of geotechnical courses in civil engineering programs. Now let me go deeper and tell you about the coverage of geosynthetics in those geotechnical courses. And I'm going to start with the coverage of geosynthetics in mandatory courses. Some heads up, it's terrible. So in Canada, over 58% of the mandatory geotechnical courses do not have a single hour exposure of geosynthetics in mandatory courses. Over 58% in India, over 58% in Turkey, over 71% in the US. Again, red is bad. Red means no exposure to geosynthetics in mandatory courses. The red is no exposure at all. Okay, I hope we do better in 5-year programs. After all, we have an extra year to graduate our civil engineers. Mixed. So Argentina, definitely better. At least a couple of hours of geosynthetics in mandatory courses. In Brazil, yes, I could say over 50% of mandatory courses of institutions offer, 50% of institutions offer mandatory courses that cover geosynthetics. And then the bad guys, or at least in the context of this research, Colombia, very little exposure. Red means no exposure at all. Germany means no exposure at all in mandatory courses. Greece did great in terms of number of geotechnical courses. 86%, in spite of the healthy number of mandatory courses, do not cover a single hour of geosynthetics. All right. So this essentially tells you back what I just mentioned, so I'm not going to spend time on this, but the coverage of geosynthetics in mandatory courses varies. 4-year programs, the coverage is minimal. In 5-year programs, there is a more diverse pattern, but essentially I would call it unsatisfactory. I could say that an important message, at least out of this, is that the length of the geotechnical program was not a good predictor of the coverage of geosynthetics. I'm going to go very quickly over the elective undergraduate courses, the coverage in undergraduate geotechnical courses, just to tell you that the presence of elective courses in 4-year programs not necessarily improved, or at least significantly, the picture. And the same goes for 5-year programs. Definitely, the elective courses not necessarily improved the picture. Some, but definitely not an important or significant additional exposure. So after covering, and this is what I just mentioned, in 4-year programs, there is definitely in elective courses, essentially the message is that elective courses do not compensate for the lack of coverage of geosynthetics in mandatory courses. There is a program that I'm not going to walk you through, but that tries to compensate for at least one of the potential deterrences for teaching geosynthetics, which is a potential lack of faculty familiarity with this program, and that is a program by the International Geosynthetic Society called Educate the Educators. And as of, this was the topic of a previous lecture that I presented 5 years ago, and at the time I did show you the countries. And right now there are 21 countries that have benefited from this program. This is the coverage 5 years ago. All right, so as far as educational strategies, since we're not doing so well, educational strategies to introduce geosynthetics to undergraduate programs. This is a slide that I show essentially to integrate geosynthetics within the family of gravels, silts, clays, sands, and geosynthetics. And I could say that the message is, or the strategy that is proposed in here is to provide an early exposure to geosynthetics as core geotechnical material. A key strategy promoted in this presentation is to introduce students to geosynthetics early. This is to cover the aspects related to the material aspects of the geosynthetics content. This brings the benefit of clarifying the concept of functions in geotechnical engineering, which essentially helps us guide essentially how are we going to choose not only geosynthetics but also soils based on the properties and their intended use. And here is an example of an exposure in a very tight program. This is the syllabus of Geotechnical Engineering, the introductory course at the University of Texas at Austin. 30 hours out of 45, simply because it has a laboratory component that accounts for 15 additional hours. Here is 1 hour of those 30 dedicated to geosynthetics towards the end of the program. I would say that the coverage of geosynthetics brings the opportunity to emphasize the concept of having geomaterials as construction materials. This is a concept that students may not fully appreciate, and thinking that geotechnical materials and soils in general are the characterization of the in situ soils. And particularly, students may become surprised in recognizing how much of the infrastructure is built using geomaterials as construction materials. So the characterization of geomaterials is not just about their classification, about the compliance, but also to select their selection, placement, and use and in the built environment. Here are the illustrations, and I'm going to go just showing you slides that I present, for example, to characterize the function of separation. That is not a function that soils have, but it allows characterizing how or conveying how important it is in some cases to maintain dissimilar materials separate. Or the concept of clays, but not only being identified as in situ materials that potentially we covered at the time of studying consolidation of clays and settlements, but also their selection as barrier materials. And in this case, complementing that with the use of geosynthetics as barrier materials and characterizing the properties that we may need. We may draw parallels between concepts that we have already covered in our introductory geotechnical course, for example, Darcy's law, when we get back to geosynthetics. For example, when covering the topics such as drainage and such as reinforcement. I could say that this is based on some reinforcing some previously covered courses, even if it was in the same course, may bring some additional opportunities for deepening the understanding. For example, here's a drainage function, but in this case, not of a gravel layer, but of a geosynthetic layer. In some cases, students may get confused because we're going to use different terminology to characterize the hydraulic properties. For example, and those that are hydrogeologists may recognize the term, the concept of transmissivity that we use to characterize a confined aquifer is the same concept that we use to characterize a geocomposite. which is the product of the hydraulic conductivity times the thickness. So, and how do we incorporate this into Darcy's law? Here's our good old Darcy's law, which is the same that we use for soils, we're going to use for geosynthetics. But we're going to try to get rid, when we specify geosynthetics, we're going to try to get rid of specifying the thickness. And we do that by lumping the hydraulic conductivity with the thickness under the term transmissivity. This is the Darcy's law expressed in terms of transmissivity. When it comes to a different function, a flow function, that is the cross-plane flow, we also are going to make good use of the previously covered Darcy's law. But in this case, using the concept of permittivity. We're going to normalize the hydraulic conductivity divided by the thickness. Why are we going to normalize it in a different way? The answer comes from Darcy's law. So when we write Darcy's law in the case of cross-plane flow, the thickness becomes part of the hydraulic gradient. And that's why we need to, when we rewrite Darcy's law, getting rid of the thickness, we need to normalize the hydraulic capacity by dividing the cross-plane hydraulic conductivity by the thickness. Very good. And what about in the mechanical side? The mechanical side is more complex to convey, but let me try. There is a concept of stiffening. And essentially what it means is that this brings the opportunity to remind students of how relevant confinement is when we deal with granular soils. So if I ask a student what is better for foundation purposes, a gravel or a clay, the obvious answer will be a gravel. And my reply would be, it depends. It depends on whether the gravel is confined or not. So, and that is something that geosynthetics may help minimize when it comes to essentially to maintain the confinement of soils, and that's what we call stiffening. I'm going to walk you finally through the thickness of geosynthetics, that we need to recognize that geosynthetics are two-dimensional materials. So in conclusions, I walked you through different components. One of them was to conclude the results of an international survey that provides insight on the distribution of geotechnical courses in the civil engineering program, significant uniformity in four-year programs, some discrepancies in five-year programs, the coverage of geosynthetics in both four-year programs and five-year programs is in the growing direction, but is definitely lacking. When it comes to the coverage of how to incorporate geosynthetics, the proposal is here to incorporate some basic knowledge on the material properties of geosynthetics very early in the program. Tapping into the concept of functions may be particularly relevant. Tapping into the concept of geomaterials as construction materials, on reminding them may be particularly relevant. And driving the parallels between the core concepts in geotechnical engineering with the same concepts in geosynthetics engineering may be particularly relevant. Finally, I'm going to tell you why the use of geosynthetics may be relevant in the teaching of soils. And I'm going to quote my good friend, Professor Pantazito. And she said, and I trust her, that understanding how geosynthetics work together with soils helped me understand better how soils work. And I'm also going to bring another quote on geosynthetics, in this case by one of the founding fathers of the discipline, Dr. J.P. Giroux. On the occasion of the 53rd Terzaghi lecture, Dr. Giroux said, and he was referring to the design of filters, geotextile filters versus granular filters, and the additional insight that learning about filters can bring when using geosynthetic filters. He said that what started as technology transfer from geotechnical engineering to geosynthetics engineering ended as technology transfer from geosynthetics engineering to geotechnical engineering. And with that, I thank you for your attention.
Thank you, Professor. We have maybe time for one question if somebody has a question.
Hello, thank you very much for your presentation. I'm Cristina Vulpe from the University of Western Australia. You have presented some plots showing the compulsory, where there are compulsory geotechnical engineering courses at various universities. And what struck me was that in USA, there were 7% of the universities that didn't have any compulsory geotechnical engineering courses, but then there were 8% that didn't have any elective courses. Is there an overlap at any university between these two? Is there anywhere in in USA, where civil engineers don't have any geotechnical engineering knowledge?
Yes. There are 7% of the institutions that, never mind that they may offer healthy number of electives in geotechnical engineering, but students have the choice by selecting electives of bypassing all geotechnical engineering courses. And that is a reality. And after I have been studying how trends are, particularly in Europe, moving to the 3+2 curriculum, I can envision that that may end up happening as well if geotechnical engineering is not part of the 3 component even in European courses. That's not something that was observed in the 5-year programs, but certainly in the 4-year programs, and I suspect that may be a risk that civil engineering programs may have. So having civil engineers graduating without any exposure to geotechnical engineering.
Okay, thank you very much. Thank you very much, Professor. Just a little gift for you from Nancy.